This is a video on finding the area between two curves. So I have two functions here. I have f and I have g. F is negative x squared plus 4x, and g is just simply 2x. And we're going to do two options, and you'll notice that steps 1 and 2 are identical. So either way, we're going to determine the intersections of the two curves. So where does f equal g? So I've got f, and I've got g. I'm going to make this, so I'm solving for x, it's a quadratic, so I'm going to put everything together on the same side. I'm adding x squared, I'm subtracting 4x. I end up with 0 equals x squared minus 2x. Now that is a factorable quadratic. I factor it, and I get my two intersections at x equals 0 and x equals 2. These are going to eventually be the bounds for a couple definite integrals. Once I have the intersection point, I need to determine which function is greater over the interval. So essentially what I'm doing, I'm going to draw the graph over here. And it helps to know a little bit about the function first. So 1, 2, 3, 4. F of x, again, negative x squared plus 4x, goes through 0, 0. It goes through 2, 4. It goes through 0, 4. And it also has these 2 points here. So it's a parabola. It looks like this. Y equals 2x, or g of x is the line that has a y-intercept of 0, slope of 2. So it looks like this goes on forever. But what we just found is that these two graphs intersect at 0 and 2. Okay, so 0, 0 and 2, 4 are the points of intersection. All right, so now determine which function is greater over that interval. So from 0 to 2, we can look at the graph here and see that f is the higher function and g is the lesser function. So what I've done algebraically here is I've picked a number on that interval, which sometimes you can pick a nice number like 1, and we plug it in. Find f of 1, and we find out that is 3. Find g of 1, we find out that is 2. Visually, we could see it on the graph, but sometimes you're not going to have a graph. You're not going to want to draw the graph because the graph is difficult. So, algebraically speaking, we know that the larger function over that interval is f. That is important. So what we can do is, I'm going to zoom way out here and look at the graph down below. If we took the area under the curve, notice they're both positive functions, right? So if we took the area under the curve of f and the area under the curve of g, and we took the area here away, we would be left with the area between the curves. So what I've done in option 1 is I have found the area of the larger function over the interval. So from a to b, in this case, f of x dx would be this definite integral. We're going to use the fundamental theorem of calculus. We're going to integrate. We're going to evaluate at 2 and 0. And we're going to get a numeric answer. So that is the area under f from 0 to 2. Then we're going to find the area under the lower function. Similar process from 2 to 0, 0 to 2 for 2x dx. Integrate, plug in 2 and 0, subtract, and we get 4. And then we subtract the greater and the lesser, and we get 4/3. That is the answer. Now, here's the alternative to that. If we look at what we used to do for Riemann sums, is we would have a bunch of rectangles, right? And we would try to make those rectangles really, really small. Well, I could imagine a rectangle, and the height of the rectangle is determined by the difference in the functions. And if I made those rectangles infinitely thin, by integration, I could integrate between here and here of the difference between the two functions. So instead of subtracting the areas, I'm subtracting the functions to get the height of those rectangles, and it becomes a more efficient process. So, again, steps 1 and 2 are the same, but I'm going to find the difference between the two functions, larger minus smaller. So in this case, f minus g. Not sure what just happened. That's great. Oh, come on now. Okay, phew. All right, sorry about that. So we are finding the difference between the larger and the smaller, so f minus g, because f is the larger function. And I've done that algebra first. So I basically come up with a new function. Okay, so essentially I'm looking at the function, we'll call it h, negative x squared plus 2x. If I were to graph that function, I have a y-intercept of 0. I have roots of 0 and 2. And when I plug in 1, I believe I get out 1. So basically, over that same interval, I'm basically now just finding the area of this function. And the area under that curve will be exactly the same as the area between these two curves. So it's essentially finding a new function that has the same area as the area between those two curves. So I have that function, I integrate, I evaluate, and I end up with the same exact answer. So that's the whole process of finding the area between two curves. Let's look at another example. Find the area enclosed by the two graphs. Now, I'm not going to show you the graphs quite yet because I want you to be able to do this without the graphs. So my two functions are 4x cubed and minus 8x, and then just simply y equals x. Again, step 1, find the intersections. Set them equal, bring everything together, so I'm subtracting x, and I get 4x cubed minus 9x equals 0. I can factor out an x, and then hopefully you can notice this is a difference of squares. Factor that down, and we get our 3 points of intersection. Okay, and right here it says, notice the graph shows 3 points of intersection confirmed by the algebra to the left. So here's the algebra. I'll show you the graph in a minute. Again, showing you that we can do all of the work that we need to without the graph. Which function is larger over the two intervals? So now there's 3 points of intersection, right? So we have intervals to check. We have from negative 3 over 2 to 0, and then we have from 0 to 3 over 2. Again, luckily we have nice numbers on those intervals. I chose negative 1 on the first interval. I plug it into f, and I get out 4. I plug it into g, and I get out negative 1. Which is larger? F. On the second interval, it switches. So when I plug in 1, I get out negative 4. When I plug in 1, I get out 1. Second interval, g is larger. Let's confirm that with the graph. So the red is f, and the blue is g. Notice the intersection points, negative 1.5 for x, positive 1.5 for x, and 0. F is larger on the first interval. G is larger on the second interval. Now for this problem, I've used option 2. And so what I'm going to be doing is finding the distance between the two equations. So I'm going to do f minus g on this first part. I'm going to do g minus f on the second part. And then I'm going to integrate each piece. So, again, from negative 3/2 to 0. I don't want to use that. I want to use this. I'm subtracting the greater function minus a lesser. Now, no matter what, if you're doing this properly, and this is truly the greater function, this will always be positive, even if your function is negative. Same thing here. If this is the greater function, the result of this will be a positive. So I've got f minus g here and g minus f here. I do the fundamental theorem. Luckily, we have a 0 in there, so it makes the calculations a little bit easier. Negative 3/2 to the 4th, negative 3/2 squared, multiplied by the 9/2. And we end up getting 81/16 for each part. And when I add those together, I get 81/8. So I'm going to just hold it here for a second. You can pause the video and you can follow along. I have a special note here. And maybe you recognized that the two functions are both symmetric. They're both reflect rotation symmetry of 180, or they're odd functions. So as we go through this side and this side, we're going to notice that there's a lot of similar values here. In fact, we end up with the same exact value, and that has to do with the symmetry. That's not always going to happen. We're not always going to have perfectly symmetrical pieces. So on this particular problem, if we had noticed that earlier, we would have been able to just double one of these intervals. But I didn't want to show that because that's not always going to happen. So you can be creative, you can be more efficient if you recognize those symmetries.